Okay, so the talk here is by Martin Vogel from Bourgogne, and it's something about non-self-adjoint operators and random perturbations.
So, thank you. Also, thanks for inviting me to give here a talk. And so, the talk will be about eigenvalue statistics for a certain class of non-self-adjoint operators, well, and in particular, like what happens if we add small random perturbations. So, two of you I know have heard most of this already, so I apologize or give you again the chance to learn something more again about it, and I hope you don't mind too much. So, yeah, in particular, we look at a specific class, one-dimensional model operator, and a certain class of random perturbations, and we'll be interested in, well, in the first two moments of the statistics, meaning like we're interested in the average density of eigenvalues and the two-point interaction. And so maybe to start off a bit, just to remind ourselves why it's important to study also non-self-adjoint problems. I mean, they appear quite naturally in many problems. For example, also, I mean, trivially in the solvability theory of linear PDEs, when we start off with a like non-normal operator, or also like if we start off with a self-adjoint problem in mathematical physics, like a Hamiltonian, and we're interested in studying the scattering poles or the quantum resonance system, we find ourselves quite quickly in like trying to tackle questions about non-self-adjoint problems, or models involving the Gromov-Fokker-Planck operator, which are quite popular to study also. So. A major issue when dealing with non-self-adjoint problems is that we have terrible resolvent control. So meaning that well, an operator P, for example, from a Hilbert space to a Hilbert space, we only have a, like this lower bound here of the resolvent norm generically, which as opposed to the self-adjoint case where we have, sorry, I don't know where to stand. Put myself here. Like, remember that in the self-adjoint case, due to the spectral theorem that we have an equality here, so we have a generic, very good resolving control. But in the self-adjoint case, the only thing that we can say is that we have this lower bound, and meaning that even like far away from the spectrum, the norm of the resolvent can be still very large. And that leads in particular to one thing, and in particular it means that the spectrum can be very unstable even to tiniest perturbations. Maybe that kind of justifies that, historically speaking, so to say, in the whole kind of has been a renewed interest in the theory of non-self-adjoint problems from the numerical analysis point of view, in particular with Lillard-Trefethen and then Lillard-Trefethen and Mark Embry, following in the late 90s. Just remember that, like in numerical analysis, if you want to compute the eigenvalues of a very large matrix and it happens to be non-self-adjoint, then you automatically calculate never like the eigenvalues of the actual matrix, but a small perturbation due to the rounding error of the computer. So spectral instability is a major deal. And then later works kind of took these ideas and also brought it to PDEs. And in particular, I want to talk about Brian Davis, Maciej Sworski, Sjöstrand, and many, many more. And so, but still a good way to quantify this zone of spectral instability is given by the pseudospectrum. So again, the idea is the spectral data itself is insufficient to describe the size of the resolvent due to the fact that we're non-self-adjoint. So what people do is like you add not to the spectrum, you add the points in the resolvent set where the norm of the resolvent is still bigger than 1 over epsilon. So meaning in particular, if you go back to the self-adjoint case, that this epsilon pseudospectrum would be just a spectrum with disks. Like to each, you can blow up each spectral point to a disk, and this can give you a tube around your spectrum. But in this non-self-adjoint case, this can take really various forms, very large. It really depends on the case. So this definition is equivalent to saying just we consider the union over all spectra, well, in particular the spectra of small perturbations of our operator, where the perturbation is smaller than epsilon in norm, or yet equivalently we can just say we'll have a set in the epsilon if it's in the epsilon pseudospectrum if it's either in the spectrum itself or we have an epsilon quasi-mode, meaning that we have an approximate solution to our problem that has the error epsilon. Okay. Yes. So, I mean, particularly from the second point of view, it's quite a natural idea to just add a tiny, tiny class of random perturbations to your problem and see what happens to the spectrum. And in particular, so this talk will be part of a kind of recent research interest following kind of considering the case of elliptic pseudo-differential operators. And in particular, one has to talk about Mitteret, Hager, Brian Davis again, Bodo, Montieu, Sjöstrand, Skorski. He's not on the screen anymore. And some people more. So just as a small example before we go to the actual core of this talk, a nice example for spectral instability, a large Jordan block. So if we think of this Jordan block matrix and the dimension n being very large, there's been considerable work on this by again Skorski, Sjöstrand, Davis, Hager, and a bit of
Sorry,
myself.
do you mean that there is row zeros at the bottom?
Ah, no, yes, there should be a zero and it's in the other way. The one is somehow moved down, yes. So it's in the, above the diagonal, there is the ones. So the Jordan block matrix, very large, and what do we know about it? So, I mean, obviously the spectrum of this matrix, all the eigenvalues sit in zero with multiplicity n. Like inside the unit disk in the complex plane is the sort of spectral instability, because there, as n goes large, the resolvent is lower bound by something exponentially.
What does it matter? It is not diagonal, yes, right? But
yes, he just observed this.
you have one.
There should be a zero below,
Okay.
yes, and the one kind of slipped down.
Okay.
And, yes. And okay. So yes, it's like so. But outside this, the closure of the unit disk, we have a good resolved estimate, so they're spectrally stable. And what happens now if we add a small random perturbation for a small coupling constant in the Gaussian matrix? We kind of expect to move the spectrum to move in the whole closure of the unit disk. And if we look at the numerical simulation, this is what happens. So this is the eigenvalues for with the Jordan block perturbed with the Gaussian matrix, and the coupling constant is taken to be 10 to the power minus 5. The dimension was 500, and we see, I mean, they kind of all explode out to the boundary of the unit disk. So, I mean, we are nowhere near of keeping the eigenvalues in a small disk around the original eigenvalues of 0. So it's a really nice example of spectral instability. So now we're going to come to the actual main character of this talk, which is the Hager's model operator. So it's a semi-classical differential operator from that 2. In particular, we are interested in this smooth function g, complex value known as 1, and we're having like with particular assumptions on the imaginary part, meaning that we suppose that the imaginary part is has exactly 2 critical points. Both of them are like non-degenerate, and so then the pH h dx is plus gx is the differential operator we're considering, and the non-self-adjointness here comes just from g, basically. And also for later reference, we'll just denote px, the small px is the semi-classical principal symbol. And so, and just to say, the natural domain for this case is just the semi-classically weighted Sobolev space. So we put here in front of the derivative of small h. And well, when calculating the spectrum, it's quite easy done. So we find that the spectrum is all located on the mean plus kh. So if I make a drawing here, I will destroy the beamer, I think. Yes. So let's just make a quick drawing. So if here is the imaginary part of g, I think of it to be something like this, and then periodic in x. This being the band, we have one minimum, one maximum, and well, if we identify this plane here with C also, here being the mean of the imaginary part, all the original eigenvalues of the problem are just located equally distanced on this line here. Sorry for that drawing. They all have distance h, but they're all on this line in a complex plane with the mean of the mean of the imaginary part is. Okay. So it should come back out. Yes. Okay. So this is why the spectrum of the non-perturb problem is originally. Then we just also this whole band, basically in this case, where we are the imaginary part of G, real part, so to say, we are calling sigma. It's the closure of the closure of the image of the symbol P. And in this case, this is the zone of spectral instability, because in the interior of the sigma we can always construct quasimodes which are H infinity precise, and even more in this case we can construct quasimodes that are in H exponentially precise. Basically, this can be just done by considering, well, if we take a Z such that the imaginary part of Z would be here, we solve the equation Px psi equals to Z, and we find that it has exactly two solutions, which we call x plus and x minus, xi minus, and t star as well. And so if we just move this here, plus and then x minus, we can construct a quasimode just by taking an exponential I phi h plus x z, where this function is simply the integral over x plus to x, z minus g by dy. So, and I mean, we're just introducing a small cutoff function that is 1, so to say, in a small neighborhood of x plus, and even like we can normalize it, introduce a normalization factor. And this thing in particular is an exponential quasimode for this problem, because the imaginary part away from, if x is away from x plus, the imaginary part of this is always negative. So we see that actually it is decaying exponentially. So, yes. So, since we can do this in the interior, and the interior meaning that we are at a fixed the distance of the boundary of this sigma that is independent of h. Okay. So if we're really in the interior, these quasimodes will be exponentially approximating, and so this is a whole the whole kind of band is the zone of spectral instability. And just to say, there has been lots of work already on this problem. So in 2006, Winter and Hager started looking at this. And there was a continuous result, further results by Bourgogne in 2008, and then also by Schwester in 2010. And so, what we are going to look at is now at this problem. What happens if we add this small random perturbation, and to introduce this class for some coupling constant delta, we are looking at the following class of perturbation operators, these Q omegas, where we basically project these EKs, just the L2. The base vectors of L2 as 1, we project on them, and the alpha JKs are complex Gaussian random variables with mean 0 and expectation 1. Okay, so this is the class of perturbation we're looking at, and they are all IID random variables. Then it would be very handy to restrict, to bind actually the Hilbert-Schmidt norm of this operator. We say it's and we find that it is smaller than some constant c divided by h with a very good probability. So with a probability exponentially close to 1. So consider that h is very small. So we have this bound with a very good probability. And in particular, with Q omega then being compact, we just have that also the spectrum of the perturbation is discrete. So in this setting, there is the result, the original result by Miller and Hager from 2006 that if we count the eigenvalues in the interior of sigma, we have a Weyl asymptotics. Meaning in particular that, so now we're in this band, the original eigenvalues here, we switch on the random perturbation, we take some set with a smooth boundary in the interior, and we're interested in counting how many eigenvalues of the perturbed operator do we find in the inside. And that is the result of Hager, basically saying that if we restrict the strength of the perturbation, has to be smaller than the power of h, with kappa being larger, anything larger than 5/2. But it should be not exponentially small for a certain in h for a certain epsilon, which is sufficiently small. The reason for that will become apparent later. But if we take this, we have with a very good probability close to 1, we in fact have that the number of eigenvalues of the perturbed operator inside of the set is given by, in first order, by the symplectic volume of the preimage of under P of this set we're taking in sigma divided by 2 pi h plus an arrow time. So, I mean, this Weiler asymptotics for self-adjoint operators is, think of the Schrödinger operator, H is quite well established. But, so in this case, we also, by switching on this random perturbation, we have it also in this non-self-adjoint case. Then there has been lots of further work on this. So, before that, look at this numerical simulation. So, again, this is the case we have. We have HD. D in this case for numerics has been just taken the discretization on the Fourier side, plus E minus Ix, which would be the function G. So the imaginary part is bound between 1 and minus 1 for this case, and here is a strip of the numerics for where we perturb again with a large Gaussian matrix. So in particular in the inside, so remember that like at the beginning the eigenvalues of this problem are just located at the mean the imaginary part, which would be here just a line on 0. So the roots also is a real line, although it's non-self-adjoint. But then by switching on the random perturbation, it really explodes into this whole part here. And so, for some further details, in particular, we took h here to be an order minus the power 10 to the power minus 3, and the delta being also really small, 10 to the power minus 12. Even for a very small perturbation, we have this really nice effect. Here, this is just a zoom on on the upper boundary region. So see, I mean, here we are still kind of in the sort of while law region, but there is something that happens if we approach the boundary. So this is obviously no more a while law. I mean, the eigenvalues seem to they align, so to say. So they are denser together, and they so to say align. So, and this region definitely is not covered anymore by the result of Hager. And in particular for the average density, I mean, in the inside we already know what's happening, but for the density we're in particular interested what happens close to the boundary. I mean, why is this so? How can we describe this alignment of the eigenvalues? Just to say, so, I mean, to say again, the result of Hager is valid in the inside of this spectral region of spectral instability, sigma, meaning that we stay at a fixed distance to the boundary independent of h. Then Bordeaux-Montieu made an extension allowing for distances going to h log delta h to the power minus 1 to the power 2/3 close to the boundary, but notice that what actually happens here is we scale still with the strength of the coupling constant. So both of these results kind of have the following property that we stay inside of the pseudo-spectrum of the perturbation. So remember roughly that the pseudo-spectrum was norm of the resolvent bigger than 1 over epsilon, epsilon being the strength of the perturbation. So the delta is naturally in the case when we have h, so to say, which, because we bound with a very good probability, the norm of the operator q with 1 over h. Okay? So, but in both of these cases, we're still inside of this pseudo-spectrum, so we never go to the boundary effect. So even in this result of Bordeaux-Montieu, we cannot, where we also have, due to this result of while law, we cannot describe what is happening close to this boundary. Then there was a more generalization to a general class of pseudo-differential operators, even in d dimensions, by Hager and Sjöstrand, and where they took also perturbation as a large Gaussian matrix, and then also for by Sjöstrand in 2009 and 10 for a multiplicative random perturbation, so normal matrix, but also like a sort of random potential.
I missed the relation between epsilon, defining the pseudo-spectrum, and the other parameters.
Yes. So when we had the epsilon, right, we said that the pseudo-spectrum is everywhere where it's 1 over epsilon. Okay? In this case, we perturbed with an operator of this form, right? This is the perturbed operator. So basically, the epsilon is given by the strength of this operator, and so we have the norm of q omega, And we bound this with a probability, we restricted our probability space to bind this by something C over H times delta. So here, because you invert, you have the delta, you have H over delta, and the double larger than sign means it.
Okay, but then in this claim, the pseudo spectrum is for epsilon.
Yes, yes, the
over
epsilon.
H. Okay, that's
Yes.
the
The absolute, the pseudo spectrum of given by the strength of the
So the resolvent is simply the norm of the resolvent of given epsilon.
Indeed. So,
yeah,
I mean,
that's
yes.
very interesting.
Okay. Okay. So maybe then continuing the questions we're going to treat then is what happened. What is the distribution of these eigenvalues close to the boundary of this pseudo spectrum, and in particular, well, what is the two-point interaction, attractive, repulsive, uncorrelated. And for this, we'll go again back to this model case and to say before, I mean, in this model case, we have a really nice resolvent control. Mostly it's a model case. And so it is given the major part of the resolvent, it grows with the kind of the imaginary exponential of the imaginary part of the action between the points rho plus and rho minus. So this is what we call these two solutions here in phase space. So this is just the minimum of the two integrals here. Where the minimum basically, because since we're on S1, it's just, I mean, here again on the other side, x plus would find again the x minus, and so it's basically where the minimum distance between the 2 points is either in this side or in this side, depending basically if we're above or below this spectrum.
What were rows?
What?
What is the row plus except?
Rho plus is the solution of the two solutions where you have like this symbol equals to 7 in phase space. So basically the resolving rows has this, and this equation is maybe quite good if we keep it. So in this case, the resolvent is roughly like the exponential of this square root of h, and also scaling with the distance to the boundary. So this is for the resolvent control. Can we continue? Yes. Also, we put some hypotheses on the strength of the coupling constant. So we again say that it is smaller than a certain power of h, and we say it is larger than the exponential times square root of h of minus the exponential of minus the imaginary part of the action at, or said like at this spectral line. Basically meaning if we go below the strength of this, the perturbation is simply not strong enough to move away the eigenvalues from this spectral line, and we still kind of want to have it in this form. Also, we can assume that the distance to the boundary is smaller. We're inside of the distance of the boundary than h log h to the minus 1 power 2/3. We're going to justify this in a moment. It's basically due to the fact that we have a very good resolving control also on the boundary of this sense sigma, allowing for this restriction here. And also just remember again that by binding the operator of the perturbation, it's basically the same as restricting the space of random variables to a big ball of radius c over h. So why can we do this here? This is basically, this restriction is due to the fact that so this result again is due to Bordeaux-Montrieux and Chastran, basically given us on the boundary Z0, so Z0 on the boundary we have this very nice resolvent control, basically meaning for every point we have a constant C is 0, such that this holds for all the Z in a, so to say, disk of radius C1 h log 1 over h to the power of 2/3 around this point in the boundary. So we can even make this C1 as large as we want to if we take h small enough. Then we have this bound on the resolvent norm, and this means in particular for the strength of the coupling we chose that on these disks, which just form a sort of tube around the boundary, that this intersecting with the spectrum we are looking at is empty. So for this we can make the restriction that we are inside at a distance of h log 1 over h to the power of 2/3 times the constant of this region of spectral instability. So, and to calculate the first intensity measure of the random point process of eigenvalues, which will give us the, if it has a density, will give us the density of eigenvalues, which is put on each point of the spectrum of the perturbed operator, we put a Dirac mass, and we define this point process, and we're interested just in the intensity, the first intensity measure of this point process. So we're taking a continuous test function of compact support in omega, and we have the result that it has in fact a density up to an exponentially small error in h. We find this density, which is of this form. So we have some small error term times this product of the two functions here, and we're going to look at those two a bit in more detail. So in particular, the psi is a sum of two psis. The first one being just the wild term that we had before. The first one is simply, so we have 1/2h sigma, and sigma is the Lebesgue density of the direct image of under P of the symplectic volume form on phase space. So this is basically the result that has already been shown by Hagel or the Montreal. And however, the two other terms have a bit more complicated form. So in particular, they have again this the relation to the Poisson bracket. In particular, they have this term here, the exponential of minus 2s. S is again the imaginary part of the action between rho plus and minus. Scaling like with 1/h times delta squared. So in particular, this means that if I pull this up, it will vanish again. Who does not see if I write something down here?
You can write it, then you can lower it. Vanish and then you go.
Perfect. So basically, there are three kind of regions of interest. What happens if the norm of the resolvent is still larger than 1/delta times h? What happens if it's roughly the same size as 1/delta? And what happens if it's much smaller than 1/delta? So those are the two regions of interest. And basically remember that we have this description of the norm of the resolvent. So in this sense, okay. So this means that if we are in this region here, that we are already still deep inside the pseudospectrum, then this part here divided by h delta squared is much smaller than 1, and it will just vanish in the arrow term of the Weylian term. We will not see it. However, if we approach the boundary of the delta pseudospectrum of this operator, then this thing here starts scaling like 1/h squared. It'll start really dominating the Weylian term. We will not see the Weyl, well, the Weyl term will still be there, but then, so to say, the arrow term of this, the first term will be given purely by this term. And if we go larger, so if we go, say it's the norm of the resolvent is smaller than 1/delta, then this part here will become important. In the first two regions, exponential of this will basically be 1 as a small error term. And but if we go much larger than this, then this part here starts growing very fiercely, and in particular, the exponential will start decaying strongly, basically cutting off our density of eigenvalues. And to make these ideas a bit more precise, we can quantify this. So, I meant to suppress this. Okay, forget about this. We have, in this case, we can actually parameterize the boundary of the delta pseudospectrum. So there exists a family of smooth functions, these curves psi plus and minus, such that there we're precisely on the boundary of this delta pseudospectrum. And we draw them with red lines. We need, like here, we have a gamma plus, and here we have a gamma minus. And it turns out that the maximum of, with respect
What
to...
do you mean by h divided by O of 1 epsilon? O of 1 can be 0.
No. So at first I meant to say that everybody should forget this term. But since you asked, well, in this notation, if I write 1 over h, 1 over O1, it's never 0, it's always positive. But this is a convention of notation.
Yes, but it's not the standard one.
Depends to who you talk. But yes, so in my notation, but well, forget this term, it's as if it wasn't there. So, but still, what this means that actually the local maximum of the density can be found in a, which again are taken on smooth curves. Again taken on smooth curves, and they are very close to these original to the delta pseudo spectrum. So in this a small tube around this region, you can find the maximum of the density with respect to the imaginary part, and in particular these curves where it takes its maximum very little. So this epsilon basically being h times the log of square root of h divided by delta, and so varying very little, and we can find them in the close neighborhood of the delta pseudo spectrum. And so with these two curves, we can quantify what happens. So there exist these three zones. In the first one, so if we keep the imaginary part, so to say, so if we restrict ourselves to a box, and we keep we stay with this box inside, away from these two curves, meaning that if we stay at a distance of h log 1 over h, and the epsilon 0 1/3 basically scales it a bit. It slightly depends on delta. So if we stay in the inside of those two curves, then the whole density will be solely given by a Wien law. Okay. If, however, we integrate a bit further on, so we go to this region here, we surpass the boundary by a log of 1 over h, scaling slightly with a constant delta and this epsilon 0 here, meaning that if we integrate up to here, further on, at a distance of h log 1 over h of these two curves, then the integral of the number of the integrated density of this part is the same as if we just integrate the y law up to the boundary. Okay, so if we include the maximum, the number of eigenvalues will be just as if we had integrated the y law up to the boundary. And in particular, if we go still a little bit further in this third zone, so meaning just we advance by an epsilon still a bit further, we're integrating in the complement. So in particular, what happens if we're integrating these complements here, then there, for any epsilon like positive, we have double exponential decay of our integrated density. So basically meaning that the maximum that we saw along these lines in the simulation, I hope I can bring it back actually. So the maximum is taken along these lines that vary very little, that can be found in a small neighborhood of the delta pseudo spectrum. And the number of eigenvalues that we find there are basically all the eigenvalues that would have been given by a y law up to the boundary, just pushed to the inside. Okay. So this is well, the density. And so just here's some simulations. This is the integrated density. Basically just cut this stripe into small boxes, counted the eigenvalues and normalized. So we go to the boundary, kind of scales fairly linearly. So this is, in this case, we are purely with the y law. And close to the boundary, when we hit this region, we have this one. Described before. Also the same here. This is basically the density, again, numerically calculated. So I should probably say that it's a normal, a mean over 10,000 realizations of random observation. In this case, the density, again, numerically, just here we are in the region of the y law, and here we have this strong bump of what goes to the boundary of where the density becomes not more like 1 over h, but like 1 over h squared. And this, in comparison, is the plot of the density that we calculated. And so we got the same, and here at the boundary we have this fierce bump.
I forgot now. Is your result on the mean or almost sure?
This is on the mean.
But this, I understand this, but your theorem,
It's all in the mean.
all in the mean.
Yes.
And what do people expect? Does this hold almost surely or other?
Yes, I would expect it holds almost surely. This is the reason I'm looking at the two-point interaction.
So numerically, could you see that?
Yes, I mean, if you want to have it on, numerically, if you want to have it almost surely, you just do a lot of realizations, and you
don't
see
average.
if each of them varies
Yeah.
really a little, then you can.
And that's what
almost
you've seen.
Yes. So for this, yes. So, but it's true that to prove the variance of this model is to be done. Yes, and here's just another one with simulation of the spectrum with delta, and this time, because remember we allowed it even to be exponentially small, so I mean, we need to get into trouble quickly, so I took a slightly larger h, but still the exponent in h exponentially small delta, and you see that the kind of spectral region is logically the same, it just moves deeper inside the pseudospectrum. And also for this, this would be the density, the kind of bump just moves slightly inside to the pseudospectrum and is higher. And here is the one last picture. Both for the same age, is plotting the density, but with deltas that become smaller if we go this. So the biggest one is blue, the smallest one is red. So we just see that kind of the smaller we make it, stays the same, but the size of the bump increases and moves inside the pseudospectrum as we expect for this density. So. And finally, to calculate the two-point interaction in the interior of this pseudospectrum, we're looking just at the two-point intensity measure given by, again, the expectation over the sum of all Z and W in the spectrum, which are different from each other, evaluated on a test function. And this indicatrix here with the ball is just to remind you that we restricted the probability space to this ball of radius 1 over h, or C of 1 over h. And basically, since this is a positive linear functional, we have by the representation theorem this existence of this positive measure, and which is called the intensity. This two-point intensity measure in this case. So some further assumptions that we make. So in this case, we will stay inside of the pseudospectrum, so we will not deal with what happens on the boundary. It's still an open question. And for that matter, we also say we do not accept exponentially small perturbations, but still the upper bound stays the same. And due to some other issues, it's a bit of an imperfect result, but we will not allow the 2 points to go closer to each other than constant times h to the power of 3/5. Okay, I mean, we will allow them to be bounded by some constant, but not closer than this.
Can you remind me what is the mean spacing between those points?
The mean spacing is given by the square root of h.
Square root of h.
So we even with this can go below the mean space.
You can go below.
But we would like to go just anything positive here, but still to be done. So in this case, we also have the theorem that for a couple large enough, it indeed has this two-point intensity measure has a density for test functions on this restricted space that is up to an exponentially small error. And to look at the properties of this density, we're going to do this in the way of the conditional density. So remember that if we're inside the spectrum, that the first intensity is just given by a wide law, basically. So here we have the density, the Lebesgue density of the direct image on the principal symbol of the symplectic volume form on phase space, times 1 over 2 pi h with a small error, which is in this case always positive. And we can look at the conditional density given in W0, just rescaling this by the 1-point density. And in this case, you see that for this region here, so if we're smaller than the square root of h, larger than h to the power of 4/7, as I said, is an imperfect result. We start to see that there is a short-range repulsion because the conditional density starts decaying quadratically. So in this term of the distance, for each we have a factor of the density of the y law, but it starts decaying quadratically in distance.
Sorry, can you go back to the previous slide?
It's a good question. Oh, yes.
So, I mean, I wouldn't say it's imperfect because but the main question I have here is your test function phi is not h dependent, right? Or is it? This is not uniform, this estimate in phi.
Dependent because you have
Yes.
dh.
Yes.
What?
You have phi in C0, dh of
Yes,
phi.
it's
So
in C0, but the O there depends on the choice of phi or not?
Yes.
Or how does this work?
The
That's
O,
what I'm confused about.
yes, with the remainder, you have some normalization.
well, no, the error term of the O depends only on the maximum normal phi.
On the maximum normal phi. Only on the maximum normal phi.
Yes.
Okay, well that's good.
So, also in the result of I didn't mention it. Sorry. Also in the result of the first density, it's the same, only on the maximum. So, well then, so we start to have this, and I mean yes, but for long range it starts to decouple basically. So if we go further,
But that's not possible, sorry, you can't just depend on the maximum. Because you can choose this, it's in phase space. My worry is if you choose the support of phi extremely small, you would get 0 on the left-hand side and something positive on the right-hand side. But maybe we can discuss it out.
okay, we can.
So,
Huh?
so if 0 is equal to 1, this is good. Don't worry.
We can discuss it afterwards. Okay. You know how we are in time. Yes. Okay. But just to finish this, well, we do have this long-range decoupling. So if we are the distance of the 2 points larger than h log 1 over h half, the decouple and the density, the conditional density just becomes the density of the 1 point. So this is that, and well, all of the density. I mean, there is a formula for all of the density up to h 3/5. If we plot it, it would look like this. So we start having here would be in the zone of where we start to decouple, and this starts to be the quadratic decay. So yes, maybe just in the last 10 minutes or so, I can quickly give an outline of the proof. So at the heart of the proof of both of them lies the choice of solution problem, which in the end will give us, I will describe what this is in a moment, but the idea is we create an auxiliary problem for the whole thing that will give us a smooth function whose zeros are exactly the spectral points of the operation. So how to do this in this case, we follow an idea of Schrödinger work of this in 2010. We choose 2 elliptic self-adjoint operators, we define them in this way, like by the adjoint of pH minus z times pH, and its formal adjoint, which we call q tilde. They have both the same spectrum, which is positive, and the corresponding this t0 squared. And from further on, we will just denote the eigenfunctions corresponding to E0 being the eigenfunction of Q corresponding to the eigenvalue T0 squared, and the same of F0 for Q tilde. And both of these eigenfunctions have this nice relation. So basically, the operator acting on E0 is just this alpha 0 times F0, similar for the adjoint, where alpha 0 and the beta 0 give the first eigenvalues. So with this in mind, we set up a Prussian problem, which is this auxiliary problem here, the calligraphy P. Basically, we introduce these auxiliary operators R plus and R minus, R plus being just a projection onto the first eigenvector of Q, and R minus being the multiplication for the first eigenvector of Q tilde. If we set up this problem, it turns out it's bijective with a bounded inverse, which we call this calligraphy E, and basically by the Schur complement formula, you can see that the idea here is that this pH minus z is invertible if and only if the E minus plus z is invertible. So in this case, well, the zeros of this E minus plus are precisely the spectrum of the unperturbed operator pH. So, well, I mean, each of those are bounded. In particular, the E minus plus is exponentially small, again going with the imaginary part of the action. And so, having done this for the unperturbed operator, since we have a small perturbation, we can do it also for the perturbed one, just using the same auxiliary operators. And by like Neumann-Series argument, we have again that it's bijective and bounded inverse. And in particular, this gives us a representation for the effective Hamiltonian for the perturbed operator. We can represent it here by the effective Hamiltonian of the unperturbed model and plus first term under a small error, where the first term here is given as basically the sum over the random variables times the Fourier coefficients of the two eigenfunctions E0, F0. So using this, so having set up this, we have again this function whose zeros are just the spectral points of the operator, and then when we look a bit further, we find that actually this E minus plus verifies the V-bar equation. So there exists an F0, so an F of sets of smooth functions such that this equation holds. In particular, this means that although the function is only smooth, but the zeros of this function behave like the zeros of a holomorphic function. And this lets us prove this formula for counting the zeros. So for the one-point density, in particular here, we can just replace the spectrum by the zeros of this function. And where psi is just a regularization of the Dirac delta. And we will get basically this formula for counting the zeros. Here's the just holomorphic derivative of this function. So I mean, this kind of formula might be more common for just holomorphic functions, but due to this V-bar equation, we can prove the same for this one. And yes, the same approach holds as well for the two-point density. So yeah, which basically lets us prove this. So small outlook before we end. So also, I mean, it might be interesting to look at the eigenvalue interaction on the boundary of this to the spectrum, because we say this is different from the behavior in the interior, and also kind of would be interesting generalization for high dimensions, and well, also potentials in a sense. Yes. So maybe we have some time for some questions, and thank you anyways for your attention.
So other questions? Or further questions? Sergey?
So if you look at the real part of the energy, do you have any restrictions? Or everything is uniform on where you put your box?
There is a small variance, but it is in this case it will just vanish in the arrow terms anyways. So in these arrow terms it is uniform. So the density purely depends on the measurement to the first order.
Jens?
So is there a random matrix model that gives you the same 2-point statistics? You can obviously start with this Jacobi matrix maybe that you had, and you add a Gaussian perturbation.
Well,
or does that not make sense?
I don't know, I must say. If we start, I mean, the problem of the Jordan block at the beginning is quite different, because there you find in the limit of n going large to the h, you will find that indeed the eigenvalue distribution is uniform on the unit circle. The distribution of eigenvalues in the interior will not scale with n, so to say.
So there is no scale, because the question is about universality, right? So that's the point, is that even if you have different problems with different spectra, that's still that the local correlation, so not the global one. So exactly, that's why I was asking about the small scale on the scale of the mean spacing between eigenvalues. On that scale, you often expect universality. So it could be that a finite rank approximation to your operator could maybe have the same statistics as you go into the limit.
I would say it seems plausible, but I did not look into this. Definitely a good question.
Other questions?
Good answer. Good answer.
Yes?
Actually, do you have a conjecture about this eigenvalue statistics at the pseudospectral boundary? Because in your pictures, it actually looked almost like clock, that they were very spaced, very uniformly somehow.
I do not have a conjecture because I mean that they seem to. I mean, if you look at some other numerical simulations, they do seem to accumulate in this really on this boundary. But then it would depend on the form of the pseudospectral
And I
boundary.
mean like directly at the boundary. I mean the ones that accumulate at the boundary. Then if you just look at these ones at this line, they somehow seem to be almost clock distributed. Like in these pictures. So I wonder, was this just these pictures, or does this always occur? And I mean, that there seems to be quite some repulsion.
In this case, so I mean, there's yet not much known about the precise distribution of the eigenvalues on the boundary. I mean, there is another good case of the Scottish flag operator, where you see there has been in a paper by Christians and Swarsky, you find that again you have a very even distribution on the boundary of the eigenvalues, and in the interior you will find a sort of wide norm. But there it's also phenomenal. They also didn't give a description of this phenomenon yet. So as I'm aware, I'm the first kind of to really look at this distribution on this boundary, and there's too many open questions. So yes.
So why don't we make a conjecture that it is uniform? If there is no conjecture, we can make a conjecture.
Is this your conjecture?
Oh, I don't know. We make it the program conjecture.
And if it turns out to be wrong, that it is no problem.
Okay. Further questions? Okay, let us thank the speaker again.